Thanks for the introduction. My name's Jorge Ortiz. I'm an assistant professor here, and I'm here to talk about our recently awarded NSF ERC for the Center for Smart Streetscapes. And so it's I'm going to give a bit of a high-level overview in some of the potential projects that are starting off now, which we're in the process of brainstorming and moving forward on this multi-year project. So, this really started from the observation that America needs cities to work for all, and that 80% of the U.S. population lives in cities, that 91% of the U.S. GDP is generated in cities, and we need to make cities more livable, to provide better quality of life, to increase safety. And we're seeing lots of different trends being coming from cities, right? The fact that cities are greener than non-urban areas. So the reason we think technology will play a fundamental role in the future of cities is because legacy infrastructure inhibits adaptation. The infrastructure takes a long time to build, and it's an enormous effort and cost to adapt. There are strained local budgets with that are insufficient unless we take a drastically new approach with the use of technology. Technology can help with rapid adaptation in the way that we use our legacy infrastructure to enable new classes of services. And through engagement, adaptation can accommodate and balance the needs and desires of all stakeholders. And smart cities are really at a crossroads in the United States. There is distrust of surveillance and the use of public space sensor data. So there's function creep. Sensors are put out into the infrastructure for some time, and sometimes the data that's collected is exploited. There are high-profile failures. In fact, there was a big smart cities project in Toronto a few years back from Google, I believe. It was Sidewalk Labs. And the community was very much distrusting of having Google own all of the data and for there to be no community feedback into the decisions that were being made. City leaders have been surveyed, and they really want digitally just governance. So having the data to help to make better decisions. And doing it in a way that is useful for the citizens and is definitely at the forefront of what local governments care about. And it's time to pivot to technology for the public good in public spaces. And so the whole positioning of this was to consider this notion of a streetscape, which is what they call the theater for social action. It's the nexus of public, private, and commercial activities. And cities are for people. We build smart cities. We want to build smart cities from the ground up. We'd like the people to play an as integral or bigger, or as big a role as the technology and the algorithms that we design moving forward to make cities smart. So some of the streetscape services that we foresee and that we will build over the next 5 to 10 years are increased crossing time for mobility impaired pedestrians. So this will involve identifying different types of pedestrians that are participating in the streetscape and allotting more time for them. Dynamic curb parking for delivery vehicles. So considering real-time local traffic conditions, routing, different prices. So if you've ever driven in the afternoon in Manhattan, you can see that there are delivery trucks everywhere, blocking streets and making it a nightmare for most drivers to get around. We're looking at haptic and AR assistive technologies for visually impaired pedestrians. And this really requires a completely new view of how we build systems that allow for low latency interaction at the level at the scale of a streetscape. We're looking at robotic autonomous systems to do garbage collection to sense waste accumulation. self-adjusting behavior of autonomous vehicles based on hyperlocal environmental conditions. So having the infrastructure give extra information to your vehicle so that it makes smarter decisions or can help make you a better driver. And we're really looking for novel opportunities for academia, community, and industry convergence. And that requires thinking about the operating system level services that would open up the streetscape for application development. And it's a model that has worked on the internet for a long time. And really the principles of a layered architecture with clean APIs is also at the fore of where we're moving towards for the streetscape. So this engineering research sensor, it's called the Sensor for Smart Streetscapes. The vision is to provide a high precision, real-time understanding and coordination of streetscapes to foster livable, safe, and inclusive communities. It's built on 3 guiding principles. The first is tech must serve the public good. All of the communities, all communities must be stakeholders, and we need to consider as we're building the technology how to bridge the digital divide, right? So it's making the case that you don't have to have all of the sensing in place personally in order to benefit from the infrastructure sensors that are in place. We want to equitably deploy the technology and train the community through deep community engagement. And that's actually a very, very large component of this ERC, different from some of the other NSF projects that we're involved in. We're one of 5 universities involved in this, including Columbia, Florida Atlantic, Lehman College, and the University of Central Florida. It involves 35 faculty, many of which are here in this room, 8 administrators, 40 community partners, and so on and so forth. It's a massive effort, and we're really excited to get it off the ground. So back to this notion of a streetscape, we all certainly experience streetscapes. It's essentially, the area in the city or in your everyday lives where you're walking through, interacting with different actors in the street, not just the vehicles and the bike riders, but amongst each other, and rethinking how we would embed infrastructure there in order to enhance livability in these situations. The Y-edge is a fundamental substrate for enabling streetscape applications. It requires high bandwidth, low latency wireless networks, which here in the WINLAB, clearly we've been working in for a long time, and there's world-class expertise. We have high-speed optical networks are really important. Thinking about edge computing and doing sensing and actuation at the edge is a must because of latency requirements. Cloud computing support, of course, is also embedded in the infrastructure. And just to give a sense of what those latency requirements are, voice over IP is roughly 150 millisecond latency. We're looking at applications that live over here on the right side of this chart, which is more, augmented reality or haptics or real-time interaction way at the edge for participants in the streetscape. Some of the thematic areas that we're exploring on the application side are road safety and traffic efficiency, public safety, assistive technologies, future of outdoor work, and hyperlocal environments. And as an example of this, consider the very common situation in Manhattan where you have a delivery vehicle that's double parked for hours and hours at a time. You have this delivery truck, it's unloading usually in the same spot every day, making it more difficult for the traffic to get around, potentially even being a hazard, not just to other drivers and pedestrians, but to the folks who live around that truck that is on for half the time, and they're exposed to more fumes. In this hypothetical situation, we'd have the streetscape identify that there is a place, a safer place for that truck to position itself, and propose a dynamically priced reserve zone or unloading zone for that truck. The truck could then position itself into that loading zone so that it positions itself there, loading paying the city to be there for and reserve it for a number of hours. We could design our routing algorithms, our traffic routing algorithms to direct traffic in different directions. It increases worker safety, traffic safety, and the time to load and unload the items. So, one of the I think one of the big benefits of working across such a large number of institutions is we have access to these amazing test beds, Cosmos being one of the three that we have access to, maybe the best instrumented one amongst the three, where we already have a bunch of infrastructure in place and a very dynamic environment in Manhattan to start to consider some of the design and engineering and scientific implications for designing the streetscape applications. One of the areas that I'm leading a team on is in considering the CS3's shared application architecture. So at the application layer, we're thinking about, well, what are the APIs? What are the interfaces? How do we specify an API that is cross-layer so that you push the demands of the application down to the underlying sensing infrastructure that's in place? And what are the resource management and models and applications, and how are those managed in real time? So you might imagine having a pub-sub architecture, a CS3 application ontology to run queries, and to stitch together the various components to enable these applications. So as an example of where this application infrastructure would come into place, let's consider two application examples. One is the adaptive crosswalk, which I've already explained. And the other one is this wayfinding app, where a person that's visually impaired requires real-time wayfinding assistance. So in the application example, each of our applications we foresee will have three phases that the application goes through: recognition, prediction, and response. The recognition consists of recognizing what's happening. Who are the actors? How is the scene unfolding over time? What are the spatial temporal dynamics? And how is that delivered to the applications that need to make sense of, to have this level of situational awareness? In doing prediction, we need models that do prediction very quickly. And as we saw in responding to a dynamic unfolding scene, having models that have some time horizon over which risk can be assessed for various different types of safety applications is going to be important. And of course, in response, we need a way of very quickly pushing a control signal down to the individual actors that require getting feedback from the infrastructure about what's about to unfold. So in the adaptive crosswalk application, we need to track people and objects in real time. We want to be able to classify the appropriate subclasses, so being able to identify that they're using an assistive device in order to cross a street, or that perhaps they are walking more slowly than the other pedestrians in the street. Some of the challenges include building a lightweight, accurate, real-time, privacy-preserving models for identification. So this is part of, the community doesn't want you to know where I am all the time, but it certainly is important to know that a car is coming while I'm trying to cross. Assessing the type of disability also may affect what kind of signal we feed back to the pedestrian. In the adaptation, this trajectory prediction, so some of these research questions are, how do we do trajectory prediction very quickly? How do we perform sub-second inference in real time so that we can make faster decisions? And there's some prior art that the team has done in this area. So again, it's almost like building this digital twin with this inference component to it, right? And that being a fundamental service in the substrate provided to applications. In the adaptive crosswalk, the response is identifying which actors should attain a signal, which one should receive a signal, and what should that signal be. If you're a pedestrian or you're a bike rider or you're on a motorcycle, perhaps it's telling you to slow down. For a car, you may explicitly force it to slow down. For a pedestrian, you might actually change the walk signal so that they have more time. You need to determine the optimal mixture of that control signal. So yes, you can tell everyone, but what's the right mix to maximize adherence to that control signal? You need to send messages to vehicles or street displays or control traffic. You need to calculate the optimal local or global control and that timing, so how it affects the broader picture of traffic and how that's unfolding in the streetscape. So in the second application, the wayfinding application, you want to be able to identify pedestrians and obstructions, for instance. So in this example, you might have someone who's trying to cross a street. You're getting them to walk from block to block. You identify high traffic areas and obstructions, and you're providing real-time haptic feedback for them to navigate the street. You may be able to push them towards actual entrances of a bus, for instance, right? So that they know exactly where the bus is opening. In the case of having inclement weather, you want to be able to use the embedded sensors in the city to recognize that some surfaces are slippery or icy, and that perhaps those shouldn't be considered, and differentiate them from clear paths. So naturally, the challenge with all of this deeply embedded infrastructure then is to build these robust dynamic maps of the physical space. And for that, we'll use a mixture of multi-sensing modes, right? So millimeter wave, RGB, IR cameras. How do you mix those in order to maximize the accuracy with which we can construct this, essentially this digital twin of the space? In some cases, how do you infuse then also the sensors that people wear on them? You know, I have a smartwatch, many people do. They can participate in providing that information to you. And boy, you can tell quite a lot from just accelerometer data about the terrain. So how do you incorporate that into the bigger picture? Some of these implicit interactions, inferring not just the direction that people are going to take, but what their intention is. Certainly, as you're walking up the block, you can turn left, right, or continue going straight. There are implicit signals, implicit body positioning and gaze tracking that we can do on the street. And it's a real challenge to do that with the current technology that we have available. And there's also a lot of work about timing. When do we interact? If you're driving down the street, what's the right time to give you that signal, right? So if we have a driving assistant in the car specifically, what's the right time to give you that signal so that your adherence probability increases? In this wayfinding act, there's a bunch of work around how to interact. Do you want audio feedback, haptic feedback? Are there new tools that we need to invent in order to provide that kind of closed loop signaling? And then, of course, assessing adherence or compliance to these control signals so that we know what the right mixture of our control channels should be. Yes, we can tell you what to do, but do you actually do it? And what's the probability, given the current unfolding of the situation, that you'll adhere to that? So having this, from a traffic perspective, even considering what the long-term physical configuration of streets should be in order to maximize adherence or minimize the effect on traffic. Privacy, of course, plays a big role, and that's part of establishing trust. So, you know, not just the algorithms for extracting, separating who from what, right? We want to minimize the personalized information, but still know more or less what kind of or what broad class of people or actors are participating and how that's unfolding. And as some examples, here's some initial work that we've already done. In a vehicle context, we've done some multimodal sensor fusion for figuring out the right time to interact with a driver. So in our data set, we asked the driver if it was a good time to interrupt them. Yes. And use the label of yes or no to infuse all of these together and try to infer what their answer will be. Here's our multi-channel, multi-sensor fusion network. We're looking at starting here and expanding it to include infrastructure sensors for making more intelligent decisions. And going back to this example of figuring out when the right time to interact will be, here's a yes example, for instance, of applying this model. Yeah. Here's a no example. No. Oh, right. We retrained this model to infer safety as well, literally just changing the labels, same model, And the question there was, of course, in this pipeline, we'd like to know when it's safe, when it's a good time, and also when it's safe. And just starting with that skeleton of doing this multi-sensor fusion and changing the safety parameters, we were curious to see when the model would disagree with what the person thought about their own assessment of the situation. So this is a not safe example. So the driver here didn't even respond because they were distracted making that turn. Here's a situation that is actually quite common in our data set. Is now the time? Right, so she answered yes, our model thinks no. Brings up a lot of interesting questions, again, with adherence, compliance, when you switch back and forth between automated mode versus suggesting to the driver that they should respond. And we've expanded. So the interesting thing about this model, just to bring some data into it, we can actually completely prevent the annoying or unsafe interruptions altogether. And in long drives, there's still ample opportunity for this type of interaction. So there is this question that this brings up about when that channel is even activated. Sure, we can register a car to say, I want the infrastructure to tell me something, but is it always the right time to activate that channel is also an open question. And we can see that actually all the extra sensing, both from the car, if we were using only the video, we'd get a 0.57 F1 score, but we went all the way up to essentially 100% with some tuning and extra sensing. So there was lots of value to having this sort of more complex view of what was happening in the dynamics. And we have a paper that was published last year on this topic. We recently expanded this model, in fact, because obviously people don't always drive by themselves in a vehicle. So again, diving into the details of how a control channel might look and how it might change the dynamics, we applied an interleaved version of this model to predict when is a good time to feed a single individual when they're who needs to be fed by a robot when they're co-dining with their friends. And this also performed quite well. So just as a basic foundational model for fusing these sensors together, that's essentially where we're starting from in thinking about how we're going to add the infrastructure sensors to this channeling. We're also looking at providing feedback to drivers directly by pointing out objects that they perhaps aren't paying attention to and should be. So here's a real-time simulation of that, where there's a model in the back end that's evaluating where the driver is looking, and if they're not looking at what we consider to be important objects that are a high risk, right? If you collide with them, our model will quickly flash a bounding box around them and say, hey, look here. You're looking at that car. You're not looking at the lady with the baby crossing the street. And we're thinking about how voice-driven interaction will change that. So, we have started taking some initial steps towards considering the full loop of adding control and having the infrastructure play a part in that. With that, I'll leave it here and I'll open it up for questions.
Thank you, Jorge.
Thank you.
We have time for maybe a naive question from a non-expert. So training works fantastic when the future inputs belong to the same data. That's well known. The unexpected input is the one that causes all the head.
Yep.
Now, if the AI or the ML is working very helpfully, it doesn't need to be dating, say.
Mm-hmm.
But if, on the other hand, you get these unexpected inputs and you don't have either human intervention or some other metric to quantify how far you are from where you need to be.
Mm-hmm.
Now, obviously, the ML couldn't know that because otherwise it would have known it wrong.
Mm-hmm.
So you have to have some external entity,
yep,
divine or human intervention, to be able to quote unquote learn.
Right.
So to bring that new input into your training data set is magic.
Yeah.
Or is hand intervention, human intervention.
So
without getting into the Bayesian network
right.
and all of that.
So the approach we took there is to assume that full automation is not the approach we're going to take, and that's precisely for this reason.
Neither, right?
Right. So in that case, if you do have a human in the loop, then you can certainly record when surprises happen and then characterize them after, of course.
Unless they're lethal.
Unless they're lethal. I mean, you could still record those and evaluate them. That's what we do when planes crash. So it's certainly useful to, even in a lethal situation, try to record and learn from it and minimize the risk later. But I suggest that in these kinds of applications, there should always be a human in the loop.
But the more fundamental question, how do you incorporate a data that is outside of your statistics and make it part of your training set for the future?
So it's not an approach that we've taken, but something we've seen, I saw recently in the literature. This is actually a very fundamental problem in the literature on autonomous driving. And what the approach that's, I would say one of the state-of-the-art approaches that people have taken is they have a simulator and they have a deep reinforcement learning external model that is adding noise to the sensors and adding noise to the situations that occur in the drive, such that it induces realistic accidents to happen. So rather than tell the sensor, drive 100 miles an hour into a wall, that's not realistic. That's very unlikely to ever happen. They add just a little bit of noise and move in the direction so as to increase the risk ever so slightly, and study specifically when a bad event happens. And actually, so they're pushing the simulation to generate samples of the rare event.
Thank you. Yes, sir.
Are you considering ever influencing regulators to force vehicle device camera manufacturers to share the sensor reading in the future?
That's a good suggestion. We hadn't talked about that, but that is it's.
We had a success. A 911 GL location was forced upon. Now every single operator, I make a call from Luna Square 911, and I get located. I'm sharing my sensor reading.
Interesting.
Cameras from Tesla being shared by whether the right impetus.
There's actually
forced to do it.
There's actually these crowdsourcing platforms now. There's an open.
But it's all crowdsourced.
Yeah, it's all crowdsourced. It's
very different from being regulated and asked
absolutely.
The feature vehicle 2030 needs to do it.
Absolutely. And I think through the sensor, that might actually be possible.
So I think the ERC is probably the kind of tool
exactly.
that might help you, the vehicle, to kind of get you to what you were saying.
Right.
You're absolutely right. I mean, when this 911.
So I think this project may be used as a vehicle to influence it.
I agree.
Yeah, you had a question.
Yeah, I was wondering about the architecture you're building here. Are you addressing, is this the same project as Anand talked about? Are you addressing kind of those
with Cosmos? It's deeply integrated with Cosmos, but it's trying to generalize.
The architecture allows kind of offloading and
correct.
And based on your timing requirements.
Correct. Correct.
Things.
That's right.
Because there are a lot of things to address. Where's the data coming from lots of devices? Where do you keep that data and on the device and so on?
And I think having an example that we're all, so these example applications are there to serve as a beachhead for exploring some of these issues. So, the wayfinding application, for instance, is one that we're actively working on now. And in fact, we just had a meeting recently to get some measurements from Cosmos to determine how much latency we actually had. And see if we either had to add extra sensing, or how are we going to figure out an algorithm to mix several models together. But all of these questions will emerge as we sort of continue exploring it through these concrete applications.
Yeah, just to be clear, these are two different projects, but many common questions.
Right.
Yes.
Yeah. We also see situations that so emphasis on safety is always first and foremost, right? But especially when you drive this with algorithms, you see situations where, for example, it's prone to more conservative decision making, right? Which means everything is going to slow down.
Mm-hmm.
So do you see like the potential for a lot of congestion? I mean, I'm studying phenomena like that.
We haven't yet. I think some of the folks who do the traffic engineering have. We haven't integrated it into this view yet. But it's an interesting one to see like what essentially the degenerative case of that, of everything being conservative and slowing down and coming to a stop.
In the old days of the early self-driving cars, we used to see these cars just stopping all the time.
Yeah.
in the middle of the road. For no reason,
mm.
and because of that, you may end up with other accidents. So
That's true. Actually, we can discuss that offline, but like there's a
from conservative decision making,
right.
But that other drivers don't expect to happen on the road.
Yeah, and there's an even broader question about the implicit signaling that you do in the way that you drive, right? Driving in Manhattan is very different from driving in New Brunswick, is very different from driving around here, you know. So even in the case where you don't slow down and come to a stop, just not signaling in time or being too slow to make a move in a place like Manhattan can also cause accidents. So it's a really complex thing to kind of examine.